Hello, everybody, and thank you for joining us today for Vertica Unify 2021. Today's breakout session is entitled Vertica in Eon Mode, Performance Improvements for Multi-Petabyte Scale. I'm Joy King, and I lead Vertica Product and Go-to-Market Strategy. I'll be your host for this breakout session. Joining me is Dave Sprogus, Senior Product Manager, and Alex Kalinin, Software Engineer. But before we begin, I encourage you to submit questions during the virtual session because you don't have to wait. Just enter your question into the Q&A box on the right-hand side of the screen. There will be a Q&A session at the end of the presentation. We'll answer as many questions as possible during that time. Any questions that we don't address, we'll do our best to answer offline. Alternatively, visit the Virtual Developer Lounge to ask additional questions and continue the conversation with our engineers and product experts after the session. And yes, this virtual session is being recorded and will be available to view on demand this week. We'll send you a notification as soon as it's ready. Please stick around to the end of the presentation to get the code and gain points to participate in our Analyze to Win competition and win prizes. Now, let's get started. Over to you, Dave and Alex.
Thank you, Joy. I'll open the presentation with a summary of the evolution of Eon Mode. Following that, I'll describe the leading edge of Eon Mode in terms of scale, which sets the stage for Alex to take us through some of the work that he and his colleagues have been doing. Alex will take us through an explanation of the performance constraints at extreme scale and how his team has addressed them. Lastly, I'll close the presentation with pointers to where you can find out more information about Vertica and Eon Mode. Let's start with the evolution of Eon Mode. Eon Mode was designed to solve the scaling problem seen in this graph of workload demand through the week. The green line tracks the workload demand, which drops on Mondays, again on Fridays, and then grows back on Saturdays. We saw customer demand for rapid scaling grow as users move their workloads to the cloud. One great benefit of the cloud is you can rent server capacity for short periods of time and then return it when your work is done. By returning servers when they're not needed, users can save money. This is an appealing feature of cloud for users with bursty and dynamically changing workloads. They can rent what they need when they need it and then return it when they do not. Why is rapid scaling a problem for Vertica in enterprise mode, and how does Eon Mode solve it? In this illustration, you can see that the database is equally distributed across the 3 nodes. Each node is responsible for a third of the database, red, blue, and green. Let's look at what it would take to scale the cluster from 3 nodes to 6 nodes. Vertica in enterprise mode must perform surgery on the segments and divide all of the underlying files of the segment. In this case, we're doubling the cluster, so we're cutting the segments in half, and we need to do this for all of the segments. Of course, if the scaling were to some other number, the file surgery would result in some other fraction. Eon Mode stores the database in shared storage, represented as the bucket under the nodes on the right. Segmentation is not governed by the number of nodes in the cluster. Instead, the segmentation count is established when the database is first created and does not change, at least not yet. In Eon Mode, we call these segments shards. In this illustration, we have 6 shards, or segments, and 3 nodes. Therefore, each node is responsible for 2 segments. Scaling the cluster is much simpler. When we scale the cluster from 3 nodes to 6 nodes, we simply change the subscriptions. When there were 3 nodes, each node had 2 shard subscriptions. Now that we have scaled to 6 nodes, each node has 1 subscription. There was no expensive file surgery, and there was no expensive data movement. There are a couple of important points to make about durability and availability. In the event a node is lost, durability is the asset property related to data safety, whereas availability is the ability to continue serving queries. Durability in enterprise mode is achieved by storing duplicate copies of one node's data on another node. We might represent this relationship like this, with the buddy copy of data on the buddy node. When a node goes down, this buddy strategy not only ensures data safety, but also ensures high availability. From the illustration, you can see that we continue to have coverage across all three segments of the database, red, green, and blue. However, we are now at some risk should another node go down. We only have one copy of green and one copy of blue. Also, our performance has gone down because one of the two nodes will be serving two segments. It is imperative to recover from this state. Node recovery in enterprise mode means restoring the node, then restoring the lost segment from the buddy node. This can be time-consuming when the database is running because the buddy node is serving two segments at the same time it is tasked with restoring the buddy copy. And we are not just restoring the lost node segment in dark blue, but also the lost node's buddy segment in green. Eon mode is quite a bit simpler. In Eon mode, the durable copy of the data is the responsibility of shared storage. The shared storage must be durable through RAID or some other approach. Each node has a subscription to one or more shards and serves them in the query process. Each node has one or more buddy subscriptions. When the node goes down in Eon mode, its buddy node will assume responsibility for serving the segment. Importantly, we're not worried about data safety because storage is separate from the node. However, we do care about performance and, like enterprise mode, when Eon mode loses a node, performance goes down because the buddy node is now doing twice as much work. In Eon mode, recovery is much simpler than enterprise mode. Simply restore the node and the subscriptions, and you are back in business. Eon mode does not require restoring the data copies like enterprise mode, which saves a lot of time. This was a huge evolutionary step for Vertica. Simplified and faster node recovery is a benefit whether or not the user wants to scale up and down for dynamic workloads. Eon mode was no longer just a benefit to users in the cloud, but also users on premises, where compute capacity is more likely to be fixed. You may have noticed that I snuck the notation of storage to the Eon mode compute nodes. Let's discuss that briefly. Eon mode has a local caching layer called the depot. As a cache copy, it is entirely ephemeral. You need not worry about losing it because the durable copy is always in shared storage. The reason for a caching layer is that shared storage is not performant, certainly not as performant as locally attached disk. In enterprise mode, both performance and durability come from the locally attached storage. In Eon mode, durability comes from shared storage while performance comes from the depot. Because the depot of a recently recovered node may take a little time to catch up, initial performance might be slow. Once the depot catches up, performance will be fully restored. Now that we've worked out scaling, what does it mean to scale past shard count? If we double the cluster, can we service twice as much workload? Yes. What's more, we can service different workloads, and we do this by organizing nodes into subclusters. Subclusters still belong to the same overall cluster. That is how they share metadata changes so that every subcluster is looking at the same fresh data. However, each subcluster works as an independent execution group. Subclusters can service vastly different workloads. The first subcluster might be servicing fast dashboard queries, while the second subcluster is servicing long-running analytic queries. Workload isolation between the subclusters means that the long-running queries in subcluster 2 will not impact the short-running queries in subcluster 1. Looking back on this chart, we can now address these workloads individually, which might look something like this. Same workloads, but each has its own capacity line. Here are those same 4 workloads, again, laid out horizontally. Here's our database sitting in shared storage. And here are the subclusters that we provision according to the demands of the workload, of each workload. We create them as needed. We take them down when no longer needed. And from an evolutionary perspective, workload isolation was another huge benefit for both cloud and non-cloud users. Turning to the last feature of Eon mode, when we have no workloads, but we want to preserve the database for later, such as the case with project work, we can hibernate the database entirely. We bring it back when we need it through a simple process called revive. That brings us to where we are now with Eon mode. On the left, Eon mode delivers Vertica with the cloud economics promise, which is to consume only what you need when you need it so that your spending is aligned with workload demands. And we achieve this through the separation of compute from storage. Separation lets you scale your infrastructure linearly up to meet increased demand, down to save money. Isolate analytic workloads so that one workload does not impact the SLA or service level agreement of another workload. Improve database operations, particularly faster node recovery, and hibernate your cluster to save money when not in service, then bring it back when you need it again. We do not explicitly list it, but as a result of the separation of compute from storage and improved node recovery, Eon mode also facilitates larger databases. And that is the focus of this presentation, pressing performance at scale. But what does at scale really mean? Where's the leading edge? And what are we doing on the leading edge? Here's a distribution of production databases run by our customers. Not all of them, just the ones that we have support data for. Along the bottom axis, I have grouped our customer databases into size brackets. Up the y-axis is the number of databases in each bracket. The numbers might be a bit small, so I'll call out a few notable ones. Starting on the left, the first bracket is 0 to 100 terabytes with about 750 customer databases. The next bracket is 100 to 200 terabytes with 50 or so databases. And the height of the bars generally goes down as you move to the right. Out at the far right, what we might call the leading edge, you can see a very small bar representing a very large database operated by the trade desk. The trade desk is our largest Eon mode customer with a database of 11.5 petabytes. As you might expect, 11.5 petabytes managed by 576 nodes is testing the upper limits of Eon mode. We work very closely with the trade desk to address and improve performance at speed and scale. Everything we do for them benefits all of our customers. Benefits include improved resiliency, faster performance, and confidence to grow. And this is where my review and background ends, and where the meat of this presentation begins. Alex is a member of the dev team working very closely with the trade desk and addressing ways to improve performance every day. He will take you through some of the challenges and evolutionary work that we have been doing at the leading edge of very large database management. Over to you, Alex.
Okay, so thank you, Dave. In my part of the presentation, I'm going to talk about the challenges we have encountered while working on Eon, the lessons we learned, and the solutions we have applied. I'm also going to talk about a couple of technical problems in much more low-level detail. So the challenges start from the cluster startup because subclusters are the main bits of elastic scalability agenda. And first, subclusters must be made consistent with the entire cluster. That means they have to receive the global state, and which, among other things, contains information about subscriptions. And then the new nodes can learn about the shards they're going to serve, the storage containers they're going to read. So this involves a non-trivial amount of information being transferred and some tricky locking. So that's important to get it right from the performance perspective. At the same time, when the subcluster enters a cluster, it remains strongly consistent, right? So we don't have any eventual consistency. We have transactional guarantees. That, for example, means that a copy query emitting in DTL subcluster is made available, or its other storage container, its data is made available in all other subclusters immediately. That means that we need to, again, transfer a certain amount of information about newly created storage containers to all the nodes involved in the cluster. And we also have to make some locking to make sure that state remains consistent. So that's also important to get right. At the same time, while remaining strongly consistent inside the single cluster, subclusters remain sufficiently isolated. And that not only means workload isolation, as Dave already mentioned, but it also means that subclusters should not be impacted by new clusters going in and old clusters shutting down. And this is important, right? Because we don't want work lost or transactions being rolled back. At the same time, this is quite challenging because, for example, a new subcluster might start during transactional commit. Another problem here is that we want to tune resources in a more customized way because subclusters might run drastically different workloads. So for this, for example, we provide subcluster resource pool so the DBAs can provision resources accordingly. This actually was an important milestone to achieve technically. Another important milestone is deterministic subscription behavior. So it's more like an evolution of thought, because initially Eon was much more randomized. For example, we had randomized subscription layouts in hope of distributing shards evenly when new nodes arrive. And even after introducing subclusters, we actually had randomized query subscription layouts, which means that when a node is subscribed to different shards, it would actually use different shards for different queries. So we moved toward deterministic behavior for two reasons, I would think. One of these is the human factor, because DBAs know exactly what shards are going to be served by which nodes. They can provision resources accordingly. They don't have to provision depot for 2 shards, for example. They can provision for 1. At the same time, from the performance perspective, it's much better because more stable subscriptions resulted in a much less amount of information being transferred between the nodes. And again, this is important from the depot efficiency perspective because each node knows which shard is going to serve, so we can tailor the depot accordingly. So in the next part of the presentation, I'm going to talk about consistency efficiency. So as I mentioned, consistency starts with the subcluster starting up, and this can be seen as a kind of two-phase process. So the first part is obtaining what we call global non-sharded state, or sometimes we call it the state catalog. So it's done by receiving this catalog, which is replicated on all nodes from the designated node called DB clerk. So after all the new nodes have obtained the catalog, they know everything about subscriptions they are going to serve. This catalog actually contains much more information than that. Information about tables, projections, schemas, and so on. But after that, the nodes can actually subscribe to the shards they're going to serve. So basically, they can learn about the storage containers they are going to read. And after that second phase is finished, which we call subscription phase, then the cluster is ready to serve the queries. So the second part, as Dave mentioned, can be seen as recovery in Eon. So it's crucial to speed up, again, because of these two factors. First, it involves quite large amount of information being transferred to the new nodes. Both global non-sharded and sharded parts of the catalog might be quite large. And at certain points during invitation, we are going to lock the cluster from all the updates. So that's important to actually make it efficient because we want to keep those locking at the minimum. One of the interesting thoughts or lessons I wanted to share here is that when you start multiple subclusters, when you start multiple nodes at the same time, we don't always want to be eager actually inviting those nodes. Sometimes we want to wait and batch those nodes up. So, for example, let's assume that we start 100 nodes at the same time. For example, we start several subclusters. And Vertica perfectly supports that, right? We can start multiple subclusters at the same time, and they're going to enter the cluster in parallel. So what if 80 of those nodes are slightly delayed? And this is not uncommon in cloud environment, which sometimes might be somewhat unstable. So we have two choices to make here. So we can wait for all 100 nodes to arrive, and then we can invite those nodes, ship the catalog to them at the same time. Or we can invite 20 nodes now, and then we can delay those 80 for later in hopes to basically bring as many nodes as quickly as possible. And to consider what we want to do here, consider this, that when we return to those 80 nodes later, we will have to pass the catalog again, and it's going to be almost the same because the non-sharded catalog doesn't change that often. At the same time, we will have to subscribe those 80 shards to subscriptions again, maybe duplicating some information passing and making locking again. So what we learned actually here is that sometimes it's better to wait for a couple of seconds and batch those nodes together and invite them in unison to make subcluster startup much more efficient. So we would wait for those 100 nodes and ship the non-sharded catalog to them. Then when they are ready, ship the sharded part of the catalog, the subscriptions themselves. And sometimes we call it batch subscriptions. So again, this results in much less locking because, for example, all the subscriptions can be made in a single transaction, and much more efficient data shipping because we know exactly how many nodes should receive the data. So as I mentioned, when the subcluster enters the cluster, it remains consistent. So we employ similar techniques to keep it consistent. First of all, when certain transactions introduce updates to the global states, those updates are shipped to all the other nodes in the cluster. So we employ cluster-wide locking to keep the state consistent. We employ distributed commits to basically make the global transactional state part of the real global state. And you can see the challenges here, the two main challenges, I would say, is the first challenge is reducing the log holding times because, those logs are exclusive. As I mentioned, they block catalog updates. So they present critical sections, and we always want to make those critical sections short. At the same time, we want to improve catalog shipping times because we cannot make anything consistent until every node has received the new data. And so for the rest of my presentation, I'm going to talk about these two issues in more detail. First, let me talk about data transfer. And to talk about data transfer, I need first to talk about spread, the framework Vertica employs, which I call here the control messenger. So spread is a framework which is used and licensed by Vertica to bring certain guarantees that are often desirable in distributed systems, namely ordered and reliable messages, which we sometimes call control messages. And I'm going to talk about those in a second. From the architectural perspective, spread is a ring of daemons, or as we call them, control nodes. And all those daemons pass the token around. So whoever has the token is the leader and can do certain things like send new messages to other nodes. Transportation-wise, spread is UDP-based because when spread was introduced, UDP was deemed more efficient than TCP. First of all, it has less overhead in general as the protocol. And secondly, when you have on-premise network, you can actually make UDP being broadcast in a hardware way. So for example, if UDP packet needs to be sent to a large number of nodes, you have to send it only once, and then it's going to be distributed in the hardware way between those nodes. And this is very efficient. Since we have multi-100 node installations, so it's important to keep the ring as small as possible, because if we have multi-100 node ring, it's going to delay for token passing, and eventually it's going to introduce delays for those messages we send. So instead, we employ so-called large cluster mode, where not all Vertica nodes actually will run spread daemons, right? Only the control nodes will do. And all the other nodes will connect to those spread daemons using TCP connections. So here, for example, at the right side, you can see that a subcluster of 4 nodes has 2 control nodes and 2 other nodes connect to those. So effectively, this creates a 2-level distribution tree where to send the data, the node first sends it to the spread daemon, and then the spread daemon will spread it around the spread ring, and then all the other nodes will download this data from their corresponding daemons. So it's important to support the subcluster isolation here as well. No node in a subcluster connects to other control node in another subcluster. So all control nodes are effectively isolated to their own subclusters. And that's done so that when we shut down a subcluster, no other subclusters are involved. Only these subclusters control nodes are going down. We also allow, since subclusters might vary drastically in size, we'll also allow tailoring the number of control nodes to specific subclusters. So as I mentioned, we mainly use spread to send messages around. And Sometimes we call these messages control messages or distributed calls, but more often dist calls. And what happens here is that we want to control nodes in distributed operations. So a designated node, usually co-initiator, would determine the list of participants for the distributed operation and would send a call, dist call to it, basically asking them to do their local work. So one example here is example 1, where the message is sent inside the subcluster, for example, to distribute query plans and make nodes execute those. Another example is cluster-wide messages, for example, cluster-wide locking or cluster-wide commits. So in all those cases, the initiator waits for all the replies, so it gets all the successes, errors. If a node goes down and detects that, and then it can make a decision of moving to other operation or maybe committing or rolling back the transaction. So it's important to notice that these calls are not restricted in size in any way, so they can carry any arbitrary payloads. So we can move information using control messages. But we obviously want to optimize this. And that's what I'm going to talk about next. So how we move all that data. To understand why we need to optimize, I want first to talk briefly about spread troubles we started encountering when we moved to the cloud environment and when we started doing these large installations. So as part of its architecture, spread actually, spreads all the packets, all the messages around the whole ring. So that means, for example, that even if we want to send a message point to point to a single node, it's still going to be sent to all the daemons in the ring. And for large amount of information being passed, that actually saturates the ring quite quickly with those UDP packets. So UDP cluster actually is much less reliable than on-premise. We have much more duplicate packages or, for example, delayed packages. And it doesn't produce any problems in the consistency department, but from the performance it's still suboptimal because those lost or delayed packets have to be retried. At the same time, in clouds, we lose hardware broadcast because clouds don't support multicast or broadcast for UDP packets. So that means that when sending UDP packet to multiple nodes, we have to send it one by one, effectively duplicating it for each node we are going to send to. Another point I want to mention here is that spread is single-threaded daemon, which is running an event-based loop. So that means when multiple nodes or many nodes connect to spread, to a single spread daemon, it might have troubles serving those nodes efficiently. And that's especially evident in large installations where we move quite close to the spread saturation point, where it actually started reducing large delays for messages. So to deal with this problem, we started optimizing traffic basically by moving data transfer from spread to the new service, which we call transfer service. And transfer service is a Vertica in-house developed transportation layer. So the main idea behind transfer service is that we need much simpler guarantees to move the data around. So we just want to move the data. So we can also employ TCP here because TCP is more efficient in clouds. So TCP already provides quite decent flow control and already provides error correction, so we don't have to care about that. As I mentioned, sometimes we need to send messages to the group of nodes, and TCP is connection-based, so we can do it only in point-to-point fashion. However, we made transfer service to support software multicast. So it builds multi-level distribution tree and ships the data in a peer-to-peer fashion where nodes receiving the data can send the data to other nodes needing that. So this is kind of similar to BitTorrent networks. So transfer service is a mature component on Vertica, and we are starting using it in many critical places. So the first place is the initial non-sharded catalog shipping. If you remember, this is the first phase of the subcluster startup invitation routine. So we started using transfer service for this task instead of spread, starting from Vertica 10.1. And as I mentioned, we basically built a multi-level distribution tree to ship the non-sharded catalog to all the involved nodes in a single operation. The DB clearly designated nodes serve as the root of this tree, and then all the other nodes can actually move the catalog. After receiving, can move the catalog to their peers. So we utilize upload capabilities of those new nodes immediately. So another application of transfer service, and when we send those catalog diffs that are introduced by operations to all the other involved nodes. So when we do it with the spread dist calls framework, we have to broadcast those changes to all the nodes. So what happens here is that when distributed operation introduces changes to the global state, individual nodes send those diffs back to the initiator, piggybacking those on the dist call replies. And the initiator combines all the diffs into a single diff and then broadcasts that diff to all the nodes in the cluster. And that comes from the Eon enterprise times where the catalog was non-sharded and basically all the nodes needed to receive this information. So you can see that it results in quite a large amount of information being transferred to all the nodes. At the same time, in enterprise, if the diff is for the sharded catalog and it belongs to the shard S, we need to ship it only to the nodes that are subscribed to shard S. So that's exactly what we do with the transfer service. So the nodes participating in distributed operation actually send the diff directly to the nodes that need those diffs. It results in much less amount of information passing to the other nodes, and it results in much better performance. So here is the result of an experiment we did in-house for certain operations like copy table, add column, and drop column. And we chose those operations because those operations often result in large catalog diffs generated. And the right bar, the red bar here, is the basically pre-improvement result, where you can see that passing the data through spread results in a kind of very poor performance. At the same time, when we start using transfer service, so the left or green bar here, this results in order of magnitude improvement. And this has been merged to master, so this is going to be available to Vertica 11. So as I mentioned at the beginning, we have two challenges to tackle. The first one is transferring all the data between the nodes, and the second is locking. So let me start talking about this. So to talk about locks, I have to talk about the main lock, the cluster-wide mutex, which is called DCLX. So DCLX stands for Global Catalog Lock Exclusive. And as the name suggests, it basically blocks all the updates to the global state to the cluster. So those updates are made by different types of queries. For example, DDL queries like create table or create projection or create schema and so on. They just introduce new objects to the global catalog. DML queries, for example, copy result in new storage containers being created. So those storage containers will eventually need to be made part of the sharded global state. And during commit, the DML transactions will take DCLX as well. Let me talk about how DCLX is taken in the cluster. So DCLX is taken using the control message sent to all the nodes in the cluster. So the initiator will send the message asking to take DCLX on behalf of the certain transaction, T3 in this example. And since this message is totally ordered, so all the queues, all the log queues are going to be consistent on all the nodes. So we don't have to care about distributed deadlocks. So you can see that T3 enters the queue in the same order on all the nodes. So initiator waits for all the nodes to confirm this as a dist call reply, and after all the nodes have confirmed taking the lock, the cluster is considered to be locked. So some things might go wrong, however. So for example, node 1 here has taken the lock and sent the reply, so everything is okay here. For example, node 2, however, might be a little bit slow for different reasons. It might have slow disk, or it might have just large CPU load. So in this case, the previous transaction is still holding the lock and the T3 is still sitting in the queue. So it's not sending the reply yet and the lock taking is delayed, which means the whole operation is going to be delayed and all the other operations piling up beyond that, waiting for DCLX lock is going to be delayed. And for the node 3, the problem is a little bit different. While the transaction T3 has taken the lock locally, the dist call reply itself is delayed. So it might happen for different reasons. It might be because of network latency. It might be because spread is saturated with all the traffic. But the result is the same as for node 2, kind of. So the operation is delayed, and the initiator cannot complete the operation and free the lock. So the cluster is going to be blocked. So DCLX can be taken during commit as well. And the main difference here is that the commit is a control message that is sent in totally ordered way to all the nodes in the system. So it's perfectly safe, perfectly consistent to make DCLX taking part of the commit routine. The main difference here is that DCLX can be taken and freed during the operation without sending the reply back to the initiator, because the commit is the ultimate operation of the transaction. So no locks have to be held beyond commit. So this is illustrated here where the node 1 actually has finished its commit routine, and some other transaction T4, the next transaction in the queue, has taken the DCLX log. So the reply sent is just to confirm that the commit has completed. So it doesn't help much to know 2, because it's still slow, it will still have pile up in the log queue. It does help to know 3, however. You can see that since it can free the log before sending the reply, so some other transaction can take the transaction T4 and do something, so it doesn't have to be delayed. And the message delay here is going to be relevant only to commit confirmation. So let me talk about these DCLX optimizations in more detail. The first thing we explore is the optimistic concurrency control. So what happens here is basically, instead of taking GCLX and doing all the work, we do the work and take GCLX and then just recheck some prerequisites. So if the prerequisites still hold, we can commit the transaction. If the prerequisites fail, we can abort it. So you can see that it results in much shorter critical section. So GCLX is taken for a much shorter period of time. And this works very well for the operations that are not very contended. For example, if we do some maintenance operations, maintenance DML or DDL transactions on a single table, we can schedule those operations so that they don't fight with each other. Another type of optimization is moving GCLX entirely to commit. And you can see that this is kind of similar in the sense that the work is done before taking GCLX, and the checks are actually pushed inside the commit operation. And we can do it, again, because all the nodes are consistent. So after they take GCLX as part of their commit routine, they can check prerequisites in a consistent way. So they will all either agree to commit, or they will all agree to abort the commit, which is equivalent to rollback. But at the same time, as I mentioned, commit time GCLX are more shielded from transport failures or transport delays. And I want to demonstrate it on another improvement study case for the tuple mover merge out operation. So we saw a customer having very large, very long GCLX queues where GCLX taking itself is kind of slow, and all the other transactions basically put in the queue waiting for the previous transactions to freeze the GCLX. At some point, some transactions experience GCLX timeout because after a certain period of time, default is 30 minutes, we have to make the decision to either roll back the transaction, or sometimes if the GCLX is taken during commit, the node has to be brought down. And when we looked at the logs, we saw a large number of merge outs in the queue, and the network was very saturated. So we had a lot of control message delays. And we performed some in-house experiments to try to simulate the situation locally, and we saw similar things. So you can see that the longest GCLX wait time is 30 minutes, so this is the timeout. And the average time is 6 minutes. And you can imagine that having 6 minutes for the critical section is a no-no. So to understand what happened here, you have to understand some details about the merge out. So merge out is a tuple mover operation that basically combines multiple storage containers into a single one to optimize reads, and actually does most of its work locally. So it determines which containers to merge, runs the execution plan to do that, but then it takes GCLX. And this became kind of film specific because in enterprise, we don't have to do that. So after taking GCLX, we do some sanity checks to make sure that the operation still makes sense, and then commit. So you can see that GCLX taken here is explicit. So we have a critical section outside the commit. And what we had here is basically nodes being either slow to respond to GCLX message, or GCLX message was delayed. And that resulted in those long GCLX queues and long GCLX holding times. So what we did is that we tried this optimization number 2 I just described. So moving GCLX to commit, to shield it from the communication troubles. And after running the in-house experiments, we saw significant improvements. So the longer GCLX time decreased considerably, the average time decreased, as you can see. And as a bonus, the copy throughput increased. And the copy throughput increased because copies are DML transactions, though they have to take GCLX at some time during commit. So since the GCLX contention reduced significantly, copy throughput increased the order of magnitude. And those results are not just in-house, those results have been confirmed with the customer in the field. So we have much more challenges, and we learn every day from large installations, but we don't have time to cover all of them. So I tried to pick some representative cases. With that, I'm passing the torch back to Dave.
Thank you, Alex. While I'm sure that everyone in our audience would love to press the limits of Eon mode, the reality is that most will not. After all, 11.5 petabytes is incredibly large and unusual. However, I'm sure that many in our audience would be interested to learn more about Vertica and Eon mode in particular. Don't feel rushed to copy the URLs below. This presentation with its links will be publicly available. You can learn more about Vertica by visiting our product overview page. You can learn more about Eon mode in particular by visiting our Eon mode FAQ page. And getting started with Eon mode has never been easier. From anywhere on Vertica.com, look for the green Try Vertica button in the upper right-hand corner. This button will take you to a page listing all of the options for getting started quickly, including cloud marketplace listings, where you can be up and running with Vertica in less than 15 minutes. That concludes the presentation. Back to you, Joy.
Thank you for listening to our presentation today. Now we're ready for Q&A. Hello, guys. Thank you so much. Every time I listen to sessions like this, I learn more and more. So I'm going to take the first question myself because it's the only one that I can answer. And that is this session being recorded and will it be available on demand? And the answer is yes. Okay, you've gotten my wisdom for this session. Now I will ask some questions that came in live, and a number of them for Alex and Dave are tied to subclustering. So let's start with the question about how the catalog is synced between all the subclusters. You know, if you have subclusters, where does the catalog reside? I think that would be a good place to start, and then we'll talk about the performance of subclustering, which is also part of the question.
Alex, do you want to take
that?
that?
Like to take that, Alex?
Yeah, I'll take that. Right. So, I mean, it has been discussed in the presentation somewhat, right? So the subclusters themselves are highly, consistent with the rest of the cluster, and that means that when we perform all the operations, all the dist calls, as I call them, right? So if the operation results in some changes to the global state, to the catalog state, this state is shipped to all the subclusters at the same time. It's part of the transactional semantics, right? So if transaction is going to be rolled back or anything, it's, the changes are going to be aborted during transaction rollback. But that's it basically, right? It's not much about it, right? So the divs are shipped during the operations, and then eventually the transaction will result either in rollback or commit, right? So on rollback, we'll just get rid of this state created during transaction, or on commit, we'll just apply these divs to the global state so that to make it the part of the global state so that other transactions can access the state.
And do you feel like it's fair to, and the number one question actually that has interest is there any limitation or performance slowdown when more subclusters connect to shared storage?
So I don't think it's about shared storage, right? So we have to consider two things here, right? So shared storage is one thing, and obviously cloud providers can impose some restrictions on the number of connections we do to the shared storage and everything, right? But usually you can negotiate with those providers to open the spigot, and they can give you much more throughput. So that's one thing. Another thing is that when we add more and more subclusters, right? I mean, we have to synchronize those subclusters with the rest of the clusters, and that kind of is tied to the question I just answered, right? About the synchronizing all that global state, right? So, I mean, I think the goal of the presentation was kind of to ensure that to show that we actually, keep improving on that, right? Obviously, having 500 nodes is much more challenging in this regard than having 100 nodes, for example, or 6 nodes or whatever, right? And so, yeah, I mean, sometimes there might be delay, but we try to make those delays kind of invisible to the user.
So that actually leads, well, there's one last question on subclusters, which is a fairly straightforward answer. Can write operations happen in subclusters?
Yeah, so there is no kind of subcluster. Well, all operations actually happen inside the subcluster, be it a query or a DML operation, right? Those are subcluster isolated. So any subcluster can run the DML queries or DDL queries.
Okay, so now we talked about very large scale Eon, and we've got a couple of questions there, as well as I think a even more relevant question. So I'm going to start with the small before we go to the large. They heard a lot about 500 plus nodes and 11 petabytes of data, but is Eon beneficial for customers currently running with like 3 to 6 node clusters? Dave, maybe that's a
I'll take
question
that
for
one.
you.
Yeah, that's an easy. It's a a slow ball pitch for me. Thank you. The answer is yes, absolutely. And if you recall the graph with the distribution of all of our databases, or at least the ones that we've done support on and we have data for, you can see that the majority of our Eon mode databases are in the 0 to 100 terabyte range, and many of those customers are running 2, 4, 10 terabytes of data with 3 to 10 nodes, and they're getting every bit of performance with those small number of nodes and a relatively small database as our largest customer with the biggest.
And speaking of that largest customer with the biggest, because this is a question that actually I never thought of, but I should have, are the 500 plus nodes VMs? And if they are, how do they handle VM migration during EXI patching? Since Vertica doesn't support, maybe it does, VM motion. Do you have to bring down the nodes? So the first question really is, for that very large customer, are we talking nodes or virtual machines?
Can we split this one, and I'll ask Alex to
Yes.
take the spread portion of it, and I'll take the NVMe portion of it. Alex, do you want to
Yep.
address the spread portion?
Well, I mean, so I guess the question is about, bringing down the nodes and everything, right? So you have to, right? But you don't have to bring everything down, right? So we are talking about subclusters being this kind of elasticity units, right? So and what might happen is basically you start bringing some subclusters down, the machines down, patching those and bringing back up, right? So as I mentioned, subclusters are pretty isolated. So bringing down subclusters should not involve, any other subclusters. Obviously, your throughput, might decrease because you suddenly have less nodes, right? So eventually, kind of, I guess you can do it like so you have to plan. The short answer, you have to plan, right? So you can't patch live, right? But you don't have to bring the whole cluster down. You can just bring it. You can just do it on the subcluster level.
Alex, I think
Dave? Yeah.
if I could infer, the question goes to the struggles that we had with Azure in the early days when the spread timeout was exceeded while Azure was updating the VM. And so the spread timeout, you were the one who implemented the extension to the spread timeout and put a knob on it. Do you want to address that?
So that was one of the problems, but that was kind of transparent patching, right? So if the patching can be done transparent by the cloud providers, right? So when they just freeze kind of the processes and just do whatever they want, and then they basically restore the process to the same state, sort of kind of hibernate, right? We can tolerate that, right? So because like the main problem back then was spread timeout, where nodes would go away from the cluster because we would assume that those nodes just went down. So we made the timeout tunable, right? So if we, for example, if the customer gets notification or something about such patching, they can increase the timeout, saying that, okay, so there might be delay like 5 minutes, during patching or something like that. At which point, when the Vertica goes back and if the cloud provider restores everything as it is, we can just continue doing what we, had been doing at the moment of patching.
Right. So it is
Okay,
important to note, though, that we have. Oh, I'm sorry. That we have the
No, go ahead,
the
Dave.
spread timeout. Oh, thanks. The spread timeout knob, which you can set higher, particularly on Azure, where you need to set it to 35 seconds. The other thing that we've noticed on AWS relates to the NVMe that comes with some of the instance types. And when AWS patches the VM, patches the host, and it moves the VM to another bit of bare metal hardware, everything that was on NVMe is lost. So you do not want to use the NVMe storage for catalog, certainly. You don't want to use it for depot either. The best use of it is for temp. Vertica requires temp space for spilling queries and other large operations. And so when that when temp is on NVMe, your performance is going to be considerably faster than if it's on block storage. Thanks, Joy.
Okay, absolutely. So now, because as always, there are more questions, I want to encourage everyone to join Alex and others in the Dev Lounge this afternoon and tomorrow afternoon and Thursday morning. And I'm speaking in East Coast time zone. So you can dive deeper and deeper into this topic and all of the other references that Dave made. I want to make sure that we respect all the other sessions that are going to start in about 9 minutes. So thank you, gentlemen. And for everyone who was participating in this session, don't forget, you have an opportunity to earn points, earn prizes, and, personal to me, make a difference in a dog's life by entering a code into the Analyze to Win platform. The code for today's session is Newfoundland, and that is spelled Newfoundland. Newfoundland is the code for this session. Enter that into the Analyze to Win platform, earn points, earn prizes, and make a difference. And then in addition, I would like you to hang around for another few seconds and hear a pretty cool story from our HPE Gold sponsor partner.
Let's face it, public cloud wasn't built to handle everything, but that's okay, because now you can bring a new kind of cloud experience to all your apps and data, no matter where they live. Meet the next generation of cloud services from HPE GreenLake, a simple, open platform built for everything from edge to cloud, all delivered as a service. If you need more, add more with a simple point and click. Get everything as a service, built to order, add services with a click, pay as you go, have it managed for you. HPE GreenLake, the cloud that comes to you.